Let me just state at the outset that this is going to be purely a review talk, and none of the work is original and not by me either. So,
well, it was original.
At some point, yes.
I'm going to tell Seiberg.
Well, I think they would also agree with that, because the work was done by mathematicians many years before Seiberg and Budler. All right, but yeah, in the same spirit, it's quite interesting to see that these kind of ideas, the generalities associated with conformal field theory, keep getting new avatars once in a while. So it's quite fruitful to study these things, even though it's work done in the past 40 years or something. So let me just begin by setting some notation. So we are going to study the representation theory of the conformal algebra in 2 dimensions, and all physical theories which possess this conformal symmetry in 2 dimensions have states which organize themselves into representations of the conformal algebra. So I will start by writing the Virasoro algebra, one half of the conformal algebra in 2 dimensions. There are 2 copies of this. Excuse me. So if one tries to study the symmetries of a quantum theory on a 2-dimensional surface, closed or with boundaries and so on, one finds that locally the set of coordinate transformations which leave the metric invariant up to a scale factor can all be generated by generators of this form, where m is an integer. Classically, these can also be realized as general coordinate transformations of the circle, in which case we won't have the second term. So the second term is can be treated as a purely quantum effect when one tries to look at quantum theories. And the relation to the circle and the 2-dimensional plane is that this algebra acts on the Hilbert space of states in 2 dimensions, which in radial quantization, well, I assume that people know about radial quantization. We can fix, so time is like the radius in the complex plane. We can fix one value of time, and it becomes a circle, and we study states that are supported on the circle, and those form a Hilbert space. And diffeomorphisms, or general coordinate transformations of this circle, then act on the space of on the Hilbert space of states. And the way we propagate the states is by using one of these operators, which is the dilatation operator, which corresponds to m equal to 0. And that gives us a way of canonically propagating the state on an initial surface to whatever radius we want. And as usual, radius goes to 0, should be interpreted as t equal to minus infinity in the theory. So that would correspond to a Hilbert space supported at a point on the plane, and that's asymptotic infinity for negative time.
Maybe just one comment on this, this business about the quantum business.
Right.
You know, a conformal transformation is the sum of, is a product of a coordinate transformation and a Weyl transformation.
Okay.
And the coordinate transformations just do have that algebra without that second term.
Right.
But things, as you say, quantum mechanically under Weyl transformations pick up some scaling which classically wouldn't, and that results in that.
Right. So a classical theory which is invariant under, say, scale transformations picks up a non-invariance under quantum, once we include quantum corrections, which is also called the conformal anomaly or the trace anomaly. And the C kind of measures how strong the anomaly is.
Yeah. I just want to say that because when I was studying this, I was very confused by, you have an algebra of special kind of diffeomorphisms, and how can quantum effects change that? And it's not changing that. It's the Weyl part that's being changed.
Yes, okay, true. Thank you. All right.
But hello.
Yeah.
Yeah, maybe a pedantic comment, but whether the diffeomorphism only is there or not, it depends on whether C is equal to C bar. Right?
Also, yes. This is one half of the transformations on the plane.
Yeah. So C is not equal to C bar, even the diffeomorphisms are not, you also have
anomalies. I
Right. Thanks. All right. So we would like to study the Hilbert space of states, or the state space, in terms of the representations of this algebra.
Sorry, maybe, so I suppose you have the Heisenberg algebra, just a bosonic thing. I mean, if I'm thinking of just constructing the L operators, as quadratics of bosonic things, I mean, it's like in a quantum field theory representative of the Virasoro algebra, which will be like L is equal to some alpha n, alpha n minus n, whatever, sum over all n. Then of course I would have some particular C realized coming out of that. So you're saying that there is a path integral understanding of that.
Yeah, you could ask, why is this whole thing a symmetry? It's a symmetry because there's a coordinate transformation which only changes the metric up to a scale factor. But it does change the metric up to a scale factor. And then the theory has an invariance which says that the theory on metric G is the same as the theory on metric G times e to the power phi. The first statement is unsubtle, at least when C is equal to C bar, because it is diffeomorphism invariance, which is preserved quite mechanically. It's the second statement that has all the subtleties. I mean, things transform under that second transformation in a subtle way, which results in this.
But all central terms can be understood. I mean, in this particular case, of course, we are very fortunate that there is an understanding of the central term that way. But let's say the central term of Katzmund. Do we have, again you will say that it's some anomaly in the path integral because of suitable current is not suitable current is not also
it would once again be some wild business.
Right.
Or in the presence of a background field which couples to that current. I mean, here in the presence of a background metric, if you rescale that metric, you get a central term. There in the presence of a background field which couples. I mean, standard.
Yeah, but perhaps I should clarify, I'm not being a general statement, just about this case. This case, I think.
Yeah. In this case, if we have, say, a free boson, we can always write L in terms of quadratic creation operators, annihilation operators. For L0, there is ordering ambiguity, and that can be captured in normal ordering constant. And once we compute the algebra of those, that will get related to C here.
Talking about this, sorry, you should go on. But
It's all right.
I mean, the freedom to add a central term, does it, just in terms of algebras, does it require an infinite dimensional algebra? Or could I not add it, in a sense, the identity in the Heisenberg operator is an example. But if I just took SO3 algebra and I added a identity, it still preserves Jacobi identity and so on. Am I being dumb?
Yeah, so you'll have to do it in a consistent way.
Can I do it?
I think there's a theorem that you cannot.
You cannot. That's what I wanted to ask you.
Yeah.
So you need an infinite dimensional algebra for central terms.
Yeah, basically the largest central the largest quantum extension of SO3 is SU2.
SU2. Right.
That's the theorem.
You can have extensions which have discrete groups there.
That's okay. At the level of algebra, they're the same.
Right. Precisely. For compactly groups.
Yeah. So you really require an infinite dimensional algebra, is it, to add central extensions?
To have a continuous parameter. Yeah, that's
Okay,
my crude understanding, but I'm not sure about the exact statement.
I'm really sorry.
Yeah, it's all right. Well, I guess this is one of the places where these questions can be. Right. Right. Okay, so we consider representations which have this property that under L0, they are charged with a particular real number called Hi, and half of the operators here annihilate the state. And the rest of the representation is built by acting on, so this is for n positive. The rest of the representation is built by strings of such operators acting on this state. This is by convention called the highest weight state, and this forms the algebra. The typical representation of the Virasoro algebra. there are many subtleties which arise when these H's are related to C's, where some of the states here have zero norm. So if that happens, in order to have a unitary representation, we need to cut out the states which start from that particular null state and carried through by the application of these generators. So those are subtleties, but for generic values of these are called the conformal dimensions, and the central charge, this representation is quite good and well behaved. So the full state space can be decomposed into a sum of a representation of this and another representation of this kind of the other copy, and this will be the physical state space, written decomposed in terms of representations of Virasoro times Virasoro. Okay. So this is kind of like the kinematics part so far. We have just listed what all states we would like to have in the theory in terms of their transformations under the algebra. But a conformal field theory is much more. It requires dynamics. But the interesting part about conformal field theory is that the conformal algebra is the constraints that arise due to the conformal transformations are so strong that most of the dynamics is also determined by studying consequences of this algebra. And that is what we are going to explore in a very particular situation where the number of summands in this is finite. So general state of affairs is still not satisfactory in the sense attempts to carry through the consequences of the algebra on a conformal field theory with state space having an infinite number of representations has not been quite effective yet.
So just number of primaries, you mean?
Yes. So these are also called primaries. The states which representations which have a highest weight state which transforms as an eigenvector of L0, and
so just C equals 1 is not a rational conformal field theory.
yes, as per the definition, yes, because there is an additional primary field in the theory which is mutually local. So let me come to fields and then I'll make that statement. But the point is, yes, as Sandeep pointed out, one could have naively an infinite number of such representations, but there might be other generators or symmetries in the theory which if we include into the algebra of transformations, these representations reorganize themselves as finite number of representations under that extended algebra. So when I say a finite number of primaries, I usually mean consider the largest extended algebra possible by adding as many generators which have nice transformation laws under the Virasoro, and then consider representations of that extended algebra. And if in such an extended algebra the number of representations is finite, then that is a rational conformal field theory. Okay. So I still haven't introduced the generators, but let's say I have a generator. Let's say I have a generator Jm. Let me write it here. Then this one can consider a state that has J0 acting on, say, H, another index alpha, which has some alpha, and the L0 eigenvalue is H. Then this J0 also has, let me see, has commutation relations such that on the right hand side, some of the quantities appearing are integers. So in terms of fields, let me just introduce fields, then it will become much easier, clearer. One can, there is, in conformal field theory, this is a fact which I have not been able to completely understand rigorously, but there is this fact called the state operator correspondence. So once we start with the state in this state space, one can always associate a local operator in a one-to-one fashion with the state. So if I have a state V in H, the statement of the state operator correspondence is that there exists an operator phi which is local associated to the state V. So it's labeled by one complex number such that when it acts on the vacuum, so the vacuum is the unique state in the state space which has 0 conformal dimension. In the limit z going to 0, it gives me back the state V. So phi is some map from the space of states to the space of local operators, the theory. That is operators which are supported at a point, such that when you act on, so that's an operator acting on the Hilbert space, take the vacuum state, act on it by that particular guy which is indexed by V. The statement is that there is a one-to-one correspondence between states V and operators like this, such that when you take z going to 0 of this resultant state, you get V. Not yet.
This statement is even true when it is not unique.
Yeah. Unitarative has to do with having an inner product on this space, which corresponds to taking adjoints of the operators, which I have not talked about yet. In fact, for this entire discussion, one can relax the constraint of unitarity and then add it as an additional assumption and then see what happens.
So this is strictly in the radial quantization kind of point of view, because if I go to the cylinder,
Right.
then of course it's not local. As I go to
It's still supported on a circle.
Past, it's still supported on
On a
the
circle.
on the circle.
Yes, but the freedom of having conformal invariance kind of tells us that that same situation can be in fact described by radial quantization, in which case the entire space of local operators is in one-to-one correspondence with states inserted at past infinity.
And once you've got a local operator in one picture, you've got a local operator. So
In
then you
the,
can put that operator.
Right.
And you don't, in general, you don't include some possible power of z on the right hand side in
Well,
seeing this equation.
well, the ansatz is that
Or that's included in the definition of phi.
phi,
Is that-
and there are subleading terms which all vanish as z goes to 0. But their behavior as z goes to another point or at infinity will have some z dependence, which we also have to be careful about with issues like unitarity and so on.
I think he's solving his phi definition. That's z to the delta.
Yeah,
plus
that's
something.
the kind of stuff.
Yeah. That okay. So one can understand this in stages. First, we start with a state which has a unique scaling, and then in that case, we can always absorb that extra factor of z into this map, and then we take linear combinations and so on.
Right, don't you think that, there are two factors of z to the delta. One because of evolution, and one because you make the transformation from the
Cylinder to the
map to the cylinder. I think they cancel. I think this is just accurate.
I mean, the statement is quite accurate as it stands, but
I'm not sure.
maybe people insert a z to the delta to show explicitly the scaling behavior of that particular state. And so.
Maybe.
Like suppose one just construct the state L minus 2, I think, on the right. You know? And you could do something. Anyway, all right.
We have to divide by z squared.
Yeah, something like that, you know. And then,
Yeah.
Maybe for primaries.
Right. Okay. So one can start with these generators and form this local operator, which is okay. So L0 sits at z to the minus 2, and L minus 2 sits at z power 0. And one can study the state that the operator corresponding to L minus 2 acting on 0. That's my V. Then the operator corresponding to that should be dz. But then one has to include this factor of z square here in order to get back L minus 2 acting on 0. So that's kind of absorbed here. Thanks. So the statement which I was trying to make earlier, when we have other extra generators acting on the state space, is that one can also form these are called chiral fields. Let's say the generators scale in a particular way under L0 transformation. let's say their dimension is hj. So then one can form this field. And when I say a nice set of commutation relations with the Virasoro algebra, what I mean is that the singularities of this operator product, let me take it at 0, scales with respect to z in this particular way, plus, where this number is an integer. So the scaling dimensions, yeah, hj, yes. So as long as these numbers are integers, this operator product is mutually local. And in that case, we can add the set of generators to the set of symmetries that we started out with. And in that case, what may happen is that a bunch of primaries under the Virasoro might combine together to form an irreducible representation under Virasoro plus these additional symmetries. It may happen that
By mutually local, you mean no branch cuts?
no branch cuts. One can see it from this equation here. All right, let me proceed. Okay, so how do we explore the representation theory of this conformal algebra? Right now we have listed a bunch of representations to form my state space. But the next thing, as the next step that one would do in a way that is very analogous to finite dimensional representations of compact groups, for example, is to see what happens when we take a tensor product of two representations. And there are nice theorems in the case of compact groups which says that any tensor product can always be written as a direct sum of irreducible representations with some number of copies. And one would like to see whether that kind of a statement can be made here. There are some subtleties involved in taking the tensor product of two representations, because if one has central terms in the algebra and one takes a naive tensor product of two representations, let me erase this part. So suppose I take two representations of this Virasoro algebra. So pi 1 and pi 2 are just, there is just notation to say that LM as written is an abstract generator, and this is in the particular, this denotes the action of LM on that particular representation. So when one takes a tensor product, we have the generators, well, let me write this clearly. So on the action of LM on the tensor product representation would naively given by this. And one when one uses the Virasoro algebra to calculate what the algebra for this is, one would get a different central charge here, because central terms add up under tensor product of representations. But we would like to stay in the same theory, which is characterized by one value of central charge. So we have to modify our definition of a tensor product for representations of the Virasoro algebra. And again, physics kind of tells us what it should be, at least one of the choices for this, which is through the operator product expansion. So the operator product expansion tells us that whenever we have two operators, local operators here, one can always study this in the limit when Z1 approaches Z2. And then there is, for nicely behaved fields, let's say phi's are primaries, the fields corresponding to primaries of the Virasoro algebra with definite scaling dimension. Then there is, it's not very hard to see that this in the limit that Z1 approaches Z2 takes this form, where this is just the sum of the conformal dimensions and terms of lower power here. So there is always a finite outer pole in this and nothing more for fields which are well behaved under Virasoro transformations. So one would like to study the action of LM Okay, so now let's take this operator and act on the vacuum. Okay.
Sorry,
Mhm.
this is the same operator,
It's
phi at Z1 and
phi at Z2.
Okay.
Now this operator acting on the vacuum is another state, and I would like to study the action of the Virasoro generators on this new state, which has two representations in it. And this is a physical interpretation of the tensor product of two representations. And one would like to study what happens when LM acts on this. And
Now
again,
in this you have transported the phi of Z1
Mhm.
from Z1 equal to 0 to some finite value by the
correct.
translation operators.
Right. So how does one realize this particular state? So one starts with phi 1. So this is called radial ordering. So one starts with the state corresponding to phi 1 at minus infinity, and then propagates that outward, and the generator for that propagation is L0, because that corresponds to scaling, such that it sits at some point which has radius mod Z1, and then one uses another operator corresponding to rotations of the complex plane to put it at some particular value of Z1. And then one again next starts with the state phi 2, and then propagates it out and puts it at some value here. In fact, one of the biggest issues here is to see what happens when the radius of Z2 crosses the radius of Z1. And there are interesting things that happen. And for a very general conformal field theory, we cannot say what exactly happens, but we can constrain the behavior of this operator product as Z1 or Z2 goes past Z1. So this is from a very operator formalism point of view, where we have to care about issues of ordering and so on. But if one uses the path integral approach, then it's quite clear what happens when that particular C number operator corresponding to C number field that corresponding to this operator is taken around the other field and so on. So there are many different approaches.
Because of the branch cuts in the
There could be branch cuts, or even otherwise it will pick up some benign factors as you take one around the other.
If all of these are like Laurent expansion, integral poles,
Okay.
then what's the problem in going? I mean, I know exactly how to take Z2 to the other, as long as I'm not crossing any branch cut.
Correct.
What's the issue?
There is no issue, but from the operator point of view, it's not clear whether these two expressions will give the same answer, because we always have to choose a radial ordering when we write down a state of this chord. But from the path integral point of view, what you're saying is right. If two fields are mutually local, then one can, even if one starts in the regime where mod Z1 is greater than mod Z2, one can analytically continue that answer to a regime where mod Z1 is less than mod Z2 without any issues.
The point is a little bit like if I were to give you the time ordered Green's functions,
Mm-hmm.
and you were interested in an out of time ordered Green's function,
Mm-hmm.
how would you get it, right? And there can be subtleties. It's a little bit like this, right?
Yeah,
You
on the
start
operator
with
side, there can be subtleties. We cannot rule them out at the beginning.
But the path integral, of course, usually computes the time ordered Green's function.
Right.
So it's the analog of that issue here.
Right.
If I understand, yeah.
Certainly. So there are,
Assuming both the fields on the same circle? for the
no,
time?
no. They are on different circles with the radius of one being greater than the radius of the other.
Wait, are you going to control the order and the radial, separately, like Sandeep was saying? Are you going to,
Mhm.
as you take Z1 past Z2, are you going
Mhm.
to flip the ordering or not in your operator expression?
I'm going to, so the convention which I choose is I treat Z1 and Z2 as 2 points on the complex plane.
If you take
So I take the
mod Z1
operators. So I take the operators such that their locations are interchanged, for example, or go past each other. But I would keep the order as the same.
order the set. So that,
Yeah.
Maybe I misunderstood.
no, it's exactly what you said.
No, it's,
Yeah.
it corresponds to what I
So,
said.
but that's something we never do in the path integral.
Correct.
That's a strange contour of the path integral.
Yes.
So we're not, that's not the thing that will be of interest to you.
Right. I mean, the path integral approach will yield its own consequences for
Or as
this kind
Sandeep
of.
said, if you just stick to radial ordered operators,
Mhm.
even in operator language, you'll get something nice and simple.
Correct. And out of radial order might be related to this, but we have to figure out what that is.
But presumably will not be of interest to you anymore.
Yes. But eventually I'm going to get to that where I'm going to interchange two operators and see what happens, especially when I have branch cuts in the
But
expansion.
you presumably interchange them in the path integral. Are you going to go away from radial ordered operators? Anyway, let's see what you do.
Yeah, okay. So I'm not actually going to do a physical change of location of the operators. What I'm going to do is relate one
One operator going around the other.
going around the other. So I already have two states in which one operator has higher radius than the other, and I have another state where that first operator has now a smaller radius. And I would like to see if these two correlators can be related. Okay, so maybe you can comment at that stage.
If every manipulation is in the path integral, then even though you don't see it, you switch the ordering when one goes around the other.
Okay. So you're saying in the path integral, it gives a manifestly time ordered object. So if I want to switch the time ordering, I have no choice but to actually change Z1 to go past Z2 as
I'm saying if
points.
you do manipulations with the path integral, you may not realize it, but you're always dealing with radial order.
Right.
If you're going to do more than that, you're doing something weird from the path integral.
Sure.
Unless
Okay.
you have a bizarre
Contour,
right?
Yeah.
Then, but okay, I don't know.
Right.
And
Okay.
typically the arguments are made within the path integral, but you're sure.
Right. Okay. So again, I can study this by replacing that particular generated by T of W, say, and then extracting that particular generator by an appropriate path integral, contour integral, which is W to the n plus 1. Let me write this clearly. So to study the action of Lm on the state obtained by acting on the vacuum with these two primary fields, at this stage it's not necessary that they are primary for this definition, is of the same thing. Where this contour is away from all the insertions and is taken to be around W equal to infinity. Okay. So now one can do standard manipulations where I take this contour. So I first add the point at infinity to make it into a sphere, and let's say infinity is at the north pole, and I have a contour which is going around infinity, and I have these insertions at some points, the finite part of the complex plane. I can lasso the contour around the sphere and reduce that. I also have an origin, let's say. This need not be just the vacuum, it could be any other state as well. We just have to insert it at the vacuum, at z equal to 0 or t equal to minus infinity. And then we'll obtain contours circling the 2 points and perhaps the vacuum, depending on what kind of fields it's at the vacuum, at the origin. And then we can go ahead and compute this and see what the result is.
So
that will.
Somewhat pedantic. So the LM becomes the contour integral where the
Is that
contour
right?
is at infinity. Why? Because
Oh.
it's inserted to the left of
Everything else. So it has to be, in radial ordering, it has to be beyond all insertions. And now I might as well just take it off to infinity, because there are no other insertions that this contour encounters. So by the way, maybe this factor is slightly, maybe there is a minus m here, because if I want to extract ln from here, I do a contour integral over dz for a contour that circles the origin, and then write z to the m dz. So to go to infinity, I might have to introduce a 1 over z, so there might be a minus sign here. The idea is clear.
Which picture?
So I'm inserting tz at tw at infinity.
Right. So, but then once you move back to this picture, it's this.
It is that? Okay.
I mean, it
The
depends
original.
which, there are two patches, right?
Right?
If you're working on this patch, then it's this.
Okay.
But in that case, the W should be 0, right? The contour is like
Yeah.
counterclockwise around 0.
Right. It's just least confusing to keep it large W and
well, I'm not sure because to actually hit w equal to 0, we have to go past z1 and z2 in that case. So we wouldn't, z1 and these 2 points where the...
No, sorry, I'm sorry. Suppose we just stuck to z
Mhm.
and made z larger. So I will make it right with
You mean w? Or z? Or write it as z, okay.
Yeah, are you in the z path? Have you done a conformal transformation or not?
No, I
Well,
think
this is still in the
First patch?
in the first patch.
Yeah, so then, what's wrong with this?
This should not be an equality then, I guess. Replacing ln by this.
Why not?
no, it should be.
Yeah, you just have to take it to the left of everything else.
Right.
So let's say the first one was at 0.1, the second one is at 0.2, you do this at 1, w equals mod 1.
Okay.
This is just fine.
I mean,
So the point is so the way I get this here is by seeing where the poles are in this integram, and that is at order Lm. And there are no other poles in this integrand, so I get Lm out of this. So let's say this is some contour which is much greater than all the insertions. And then I look for poles in W of this whole operator product.
Is
There
your,
are
vacuum, is your vacuum just a vacuum?
For now it's just a vacuum. Yeah.
Okay.
It's the identity operator inserted at z equal to 0.
Yeah, so the only poles you get is when
W hits Z1,
Z1,
W hits
Z2.
Z2.
The poles hitting the vacuum are not there because
It depends on M. So if M is a negative, then there could be poles from this hitting the vacuum as well.
Okay, could be poles.
There could be, so there are these small modes which correspond to some part of TW that still does not annihilate the vacuum,
Okay,
but
you get some.
still get a pole, yeah.
But still, I think this is just okay.
All right, okay. The idea is to replace Lm by its corresponding.
I mean,
field.
for me, the definition of LM
Mhm.
is within a path integral.
Okay.
Do a contour
Okay.
and use Cauchy's theorem
Mhm.
to invert that.
Okay. So
So
when we use
contour
Cauchy's
integral-
theorem. Mhm.
Contour integral of Tz it was well defined within a path integral.
Right.
And for me, the definition of Tm, I thinking only in terms of path integrals.
Okay.
The definition of Tm,
Mhm.
Ln, is the manipulation of that contour for Tz that
Such that-
inverts this expression. That's all.
Okay.
yeah, I agree. With that, this is what.
Okay.
Yeah.
So we expand Z not around Z equal to 0, but at some point where it's inserted, and then just do a contour around that. I guess that's what he's saying.
You know, this whole expansion, anyway, we should, this is all philosophy, we should talk. My
But I
opinion
guess
is
this is the time
it's a
to.
mnemonic to remember what you have to do.
Okay. Okay.
No, but even the way you were thinking, if you first do it around infinity
Mhm.
and then you change coordinates, you will get exactly this.
Yeah.
Well,
I mean,
let's just do it. So if I take W equal to 1 over Z.
sorry, no, go ahead. If you want.
No, it's.
I just want to warn you, Naveen, that there's a finite time.
Yeah. How much time do
Go
I have?
ahead, go ahead. Go ahead.
Oh, I'm already at 45 minutes. All right.
We're eager to hear about the B matrices and F matrices.
Right. Okay.
Sorry.
No, I'm sorry.
Good.
No, I think it's just this sign which flips because dW gets a 1 over Z square and T gets a Z square out of that.
Yeah, so in the other patch it would flip sign.
It'll flip
But then
sign.
when you undo that, you come back to this as Sandeep was saying.
Right. Okay. Yeah. So what we have to study is this operator product, which I will write here again. And to study also perhaps in the path integral formalism and so on, let me also just put a state at z equal to infinity and study it as a correlator. Right. So now we know where the poles of this correlator are. It's a 3-point function, and we know that conformal invariance constrains this 3-point function. All right. So what? So it gives all the poles of this expression, and now it's a simple matter of just doing this contour integral here to extract the action of Lm on that. So if we go ahead and do that, what we get is the following. We certainly get a term which looks like this, but there is an additional tail of an infinite number of generators of higher and higher order in M, which follows from the OPE. So I cook up this notation, and let me also put this to be 0 right now, and this at z for simplicity. So then the action of Ln is given not just by one tensor Ln plus Ln tensor 1 on the tensor product of the representations, but it has this additional tail which I'll write as follows. So these expressions themselves can be found very easily after doing the contour integral, but the point is that this is continued here, z to the n minus m. All right. But the point is that there is an infinite tail here which conspires in such a way to cancel the additional c that we would get if we just used this plus this.
So what is this notation vector c0 means what?
So it takes an abstract generator and gives the action of the abstract generator on two copies of representations. So right now this is still an abstract generator. So in mathematical terminology, one would call this as a coproduct. So it just takes one generator and then gives a splitting into two, which acts. So let's say Ln acts on the algebra Ln is given by A, which is Virasoro in our case, but it could be extended with currents. So this would give an element in A tensor A. One would then take this and plug in the appropriate representations.
But are you saying that the representation of Ln on the tensor product is not identity cross Ln plus Ln cross identity, but this more?
Yes, there is more corrections.
So here there is a term, of course, when m is equal to n, which is Ln cross identity, but there's other
Precisely.
stuff. That is the correct way
Yeah.
in which it acts.
At least that's the way which OPE predicts that the Ln will act on the representations.
And what is the information regarding the representation of the operator?
So right now there is nothing. So like I said, you also have to now take Ln to be in pi 2, this Ln, and this Lm to be in pi 1. So this is a formal object which depends on one complex parameter, and it takes a generator in the algebra and gives a generator in the tensor product algebra.
Naveen,
Yeah?
a question.
Uh-huh.
So the reason you don't have an infinite sum in the first term is because one of them is at 0.
Yes, yes. We would have
In
additional terms here which will also form. It depends on what kind of n we are looking at. By the way, there is an analogous series for the other generators Ln as well. And depending on the value of n, there might be just a finite part, additional part to this, or an infinite series. It will all arise directly out of the OPE. I'm just not doing that calculation because it will take a lot of time to do it on the board. But yes, you're right. One can consider this to be at two general positions. And then in fact, by using translation invariance, we can just generate that expression from here.
And this formal parameter z, I mean, are you going to give some interpretation to it?
Well, from the physics point of view, the point is this corresponds to inserting an operator called the chiral vertex operator, which is what I'll be talking about next. But just from the algebra point of view, this z a priori seems to be an additional parameter that everything seems to depend on. But there is another place in mathematics where such these complex numbers arise, which is in the theory of quantum groups, a quantum Yang-Baxter equation, which also depends on the spectral parameter. And there is a relation of this to that.
And suppose I take n as z goes to 0.
As z goes to 0, okay.
Then it formally looks like the terms with the smallest values of m dominate.
Yes.
Is there some simplification? Does it diverge in that case? So
Yeah, it's supposed to be a Laurent expansion, so it will diverge for all values of m greater than n.
But suppose n was sufficiently large so that it didn't
okay.
diverge. Then can I literally set z equals 0? I suppose that's the question.
There is always a divergent piece because m goes up to infinity.
M goes to infinity makes it. Oh yeah, yeah.
I mean that n plus 1 choose
Yeah.
m plus 1
Yeah.
you interpret in some way where even if
I see.
Well, wait. Let me just
or
see.
is it
No.
cut off at
I
n?
think I made a mistake. This is n, so that's finite. Yeah. So in that case, you can set z equal to 0.
And this is somehow the case where there's no singularity in the equation.
No, in that case, there will be. It will just reduce to this expression for the co-product, because there is a piece which corresponds to m equal to n, and this will remain when I take z equal to 0.
I was just wondering that usually in quantum field theory it's a singular thing to set
Two operators on same point.
but it looks, or maybe there'll be some divergence.
For these generators, there is no divergence, but there is. Let me just record the expression for the other one, just to contrast between this. So I again have 1 times L minus n plus. Now this has an infinite. By the way, this minus 1 is related to the conformal dimension of T, which is 2. For other currents, there will be a shift appropriate to its conformal dimension. All right. So for these generators, for example, so this is for n greater than or equal to 2. Minus n.
So now it looks like n is always greater than m, right?
Where here?
In your z to the power.
Yes. Yeah. This is for the generators, which usually do not annihilate. The L minus 1 annihilates the vacuum, but the other ones give
So
the
in
representation
that case, you
corresponding to
always
the.
set z equals 0,
Yes.
and you get a simpler expression. Then what is
Then
it?
it's just the usual like this.
The usual splitting of
Then it's 1 tensor L n
plus L
L
tensor
tensor.
1. L tensor 1.
Okay. So I thought that was the thing you should not have been allowed to. I didn't understand. I thought you were saying that would have led C to C1 plus C2.
No, the vacuum. So that would correspond to both the operators on the vacuum, right? And we know that
Okay.
L minus 1 onwards annihilates the vacuum as well.
Okay.
L minus 1 and above
Okay.
the vacuum. So I wouldn't expect a singularity in that case.
You don't expect singularity, but I thought you were saying that it had to be different from the naive product.
No, I think what he's saying is that there are regular terms in that one. Keep the regular terms, but there are singular terms in this one.
This one.
The other one.
So to see the central charge, we need to have equal and opposite indices for the
N is
L's.
positive up there. N
Yes,
is
greater than minus 1.
Thank you.
And n is less than equal to minus 2 if, here in that same
And then it goes
notation.
to infinity. I see.
Yes.
Right.
So we need to take one generator from here and one generator from here to see the central charge.
Thank
Okay. So these expressions can also be found in this paper by Geberdiel called, I think it's called fusion product for conformal field theory, or the tensor product of representations as a fusion product for conformal field theory in the early 90s. Okay.
So is that second line L minus 7?
L minus, so this, no, this is n. Yeah. Okay. So operator product expansion now gives us a prescription to take tensor product of two representations. What we would like to do now is to study the Clebsch-Gordon coefficients of this. And those are called the chiral vertex operators. So by the way, when I have two representations and I take this fusion product, which is basically this followed by the usual tensor product of the two representations, and I denote it by just a cross. There is again a direct sum of representations, and some representations appear depending on ij and some do not. And in general, the number of times that pi k appears in this fusion product will be denoted as nijk. So I have I and j combining to give k, and this is a positive integer. These are called the fusion rules. So if I start with two primaries and then combine them, one would like to see how many times a third representation appears in that combination. And the fusion rules is one step ahead, the next step in specifying the kinematics of the theory. So what happens when you bring two representations close together? How do they split up? Okay.
Purely group theory.
Yes, with this added thing of
With a definition.
with a definition. Yes.
This is called what?
These are called the fusion rules.
So, Naveen, one
Yeah.
question. So this particular delta you have written for this Virasoro generator,
Right.
how does it have a nice form if you write in terms of T's?
In terms of
Acting on the T of Z, I mean the energy momentum tensor. This is in terms of ln.
yeah.
But
If I just
if I put some W on both sides and sum over,
okay.
is there some particular thing? I mean,
I have not checked it. I have not checked it, but yeah, there could be some nice expression where I have z to the n minus 1 w to the m, n minus m w to the m, so that might be combined into a binomial expansion maybe, and can be written in terms of the chiral field. All right.
So this also tells you how to combine the energy momentum tensor somehow of two energy momentum tensor.
Right.
If you have some two sectors.
Okay.
Is that? I mean, there I would think that it just adds, but.
Oh, you mean the central charges should add there? I didn't get the last point.
Yeah. So I'm trying to understand what this particular series does. So
Okay.
the statement is that if I take LMs and LNs which from coming from this formula,
Okay.
and if I calculate the central charge will be same as the central charges of each representation.
Yes.
Is that the?
Yes.
So the sum makes sure that the central charge doesn't add, but it just
Remains the same.
stays the same.
Yeah.
That is that right?
Yes. Correct.
Okay.
So there is a braid group point of view to this, where z acts as the spectral parameter in that case, and again there you can see that whatever corresponds to the central charge remains the same under taking a tensor product of two representations of the braid group. Okay. How much time do I have?
I mean, sorry, again. So let's say, like if I just take a fermionic theory and a scalar theory,
Okay.
or with same central charge, and if I add them up this way, what would I get? I mean, just to get an intuition of what these rules are telling me, or even two scalar theories.
Two scalar
let's say-
theories.
Yeah, two scalar theories of same key.
Okay. Okay.
And if I just add them up this way, I would get what? I would get.
No. This acts in the same theory when I take two different or the same primary and tensor them together. If I add two theories, then certainly the central charges will add up. We would like it to change.
But how does this formula know that it is in the same theory or not? What does same theory mean? I mean, it's just some representation theory.
Yeah, from representation theory, we know that this ln here and this ln here have the same algebra, right? Including the central charges. So when we, this is kind of like saying when I take SO3 and I look at a tensor product of two representations, when I take the generators to be identity times j plus j times identity, those two j's come from the same Lie algebra. Of course, there are no subtleties, but
they can act on completely different spaces, right? You are just defining. So you
certainly,
have two
yeah.
representations.
Yes,
acting
of
on
the same
completely two
algebra,
different spaces,
right?
and then you are trying to define something on the tensor product.
Yes.
right?
Yeah.
So I can in principle take a a Hilbert space of one scalar and Hilbert space of second scalar with the same central charge, so that
Okay.
the algebra is the same.
Right.
Okay.
Okay.
And try to tensor them like this. And just try to ask what will it give me? Will it give me something? It will just give me one copy of the scalar, or what is the?
No, but the central charge is actually the central term in the algebra is proportional to the identity operator in that algebra, right? So when I take the sum of two scalar theories, that term has that central term will result from adding two different identity operators corresponding to the two theories, right? So it will be a direct sum. So it will be an enlarged matrix with
Okay.
m plus two infinite dimensional identity matrices, but with C1 and C2. In this case, C1 and C2 are the same. So it will enlarge the representations instead of just combining them.
Oh, okay. So you think I should just think of central charge itself as an operator.
Yes,
Identity operator.
which commutes with everything.
Okay.
Yeah. Yeah, the statement is that C is an operator which commutes with everything, and then we can show that C is constant on all representations of this algebra, which is then written as a number. Once we impose unitarity, then there will be constraints on C saying it's positive, but at the stage of the Virasoro algebra, C can be any complex parameter, I guess.
Okay. Yeah.
All right.
Good, 1 hour. I would say 1 hour.
From now? Okay. I hope that's sufficient to at least get to the punchline.
Yeah.
Right. All right. So if there are no further questions, I would like to continue. All right. So we would like to study this, what happens on the right-hand side when we take the fusion product of two representations. So if this number Nijk is non-zero, so one might ask, we really do not know what these Nijks are when we just specify the representations. But this is from the point of view of classifying theories. And what we would like to do is assign all possible values to these n's and then carry through and then see at the end whether there is some inconsistency with these. So if there is a particular set of ni's which satisfies everything that I'm going to say next, then that is a candidate for a holomorphic half of the conformal field theory, or one chiral half. So at this stage no, n has to be a positive integer because it just counts the number of representations that appears on this, right? From this point of view, it's quite clear what Nijk should be. And in the spirit of classification, we would like to assign all possible values for Nijk and then see what happens. So I assume that I know Nijk at this stage. At the end, I might just have to discard that particular set of values if it's not consistent. Right. I'm emphasizing this point because there are other approaches where these Nijks can be calculated by the behavior of the conformal field theory on the torus and so on. It's also called the Verlinde formula, in which case these Nijks are not assumed to be known, and the behavior of the characters on the torus fix these Nijks completely.
But let me just request, just to make sure again, that these Nijks are purely group theory.
Yes.
By which I mean, if you have two theories with the same algebra and two same representations, there could be different theories, but Nijks have to be the same. For instance, just Virasoro, left half of the Virasoro algebra.
Okay. With one value of C.
With a particular value of C.
Okay.
And you've got two different operators with the same delta, the same H.
Okay.
H1 and H2. Then the Nijks are purely just fixed by Virasoro.
Yes. Yeah, or the extended symmetry.
Yes.
But it's a purely representation theoretic object. Yeah. Once we fix all the data that goes into defining the symmetry algebra,
right,
including central extensions,
yes,
levels.
Once you know your algebra, there's no physics. This is purely
precisely. Well, I would say it's the trivial part of the physics, which is kinematics.
Yeah.
Okay. So if this Nijk is non-zero, then one can do what one usually does in finite groups. That is, we take the tensor product of two representations. So these are the maps which take the operators to operators that act on the representations, and these, I'm just clarifying the notation that this represents the state space on which the operators act. And we would like to project it onto the representation hk if nijk is non-zero. Right. And I define these intertwiners here, which they are also called intertwiners or Klebs-Gordon coefficients, by following the prescription which I just said. So first I apply this coproduct to the generator, and then I apply the tensor product of the appropriate representations. So this intertwiner also depends on two complex numbers. Due to translation invariance, I can make it just one. All right. And it depends on the representations that are fusing. So there is a freedom here of choosing where the various indices go. And different texts have different conventions. So this way of writing it says that I and j combine, I being at z and j being at 0, to give a representation in k, to give a state in k. Okay.
It's some differential operator or something like that.
It's a local operator.
So I'm acting on one field inserted at z, the other field inserted at 0.
0.
And you will take derivatives with respect to z, or multiply, or integrals over.
Right.
What kind of things do you roughly do?
Well, these are quite singular objects, because we should remember that apart from doing those things which you just mentioned, we are also taking a projection to a single representation.
Yeah, I was wondering how you could do that in practical terms.
In practical terms, so these are formal objects. We cannot write down. It's not. Well, I have not seen an attempt to write down these
What about the
operators.
Casimir condition? If we were in normal group theory,
Mm-hmm.
you project onto a particular representation
Yeah.
by demanding that the Casimir is the radical.
Right.
Okay. If we were doing SL2R group theory, we could just put the Casimir condition.
Correct.
That would be a differential operator.
That would be a differential. So there are differential operators as well.
But now I want to know whether there's an analog of the Casimir operator to project onto a representation of the Virasoro.
Let's see. You see. So this is like capital J in angular momentum.
Right, like
Which
capital
is
J.
J1 plus J2.
Exactly. So in angular momentum, as you said, what we will do is J1 plus J2, the whole thing squared,
Right.
minus the eigenvalue you want.
Correct.
And that would project onto the representation you want.
Right.
Is there something similar you could do here? I mean,
I'm not aware of these.
Okay.
That.
So can I just ask something very dumb? I mean, suppose I'm just doing the OP.
Okay.
I take the primary, let's say,
Mm-hmm.
which corresponds to HJ
Okay.
at the origin. I
Yeah.
take,
Primary, yeah.
HI at Z, right?
Okay.
That whole, that product acting on the vacuum
Mm-hmm.
will create a state.
Yes.
Can't I just say that is the state in HK that I produce?
So that state belongs to the state
yeah.
space. I project onto
You
HK.
you project onto that primary and all its descendants.
Right.
And that is the state.
But how do you do the projecting onto all its descendants?
You mean mathematically?
Meaning, suppose I give you the full operator. I give you phi 1 at Z, phi 2 at Z.
If I don't know the rules of the game. If I know the OP and so on, then of course I know which
precise state.
states I'm getting with what coefficients and so on. That is how I do it.
Right. So there is no simplifying feature like a Casimir, which is constant on the representation and so on.
You have
Apart
to
from
solve
this
for the
central
whole
charge
block or
and-
whatever
To get each term.
like that.
Yeah, but yeah,
You're saying, okay, is
Yeah.
there something nice?
yeah.
Okay. So this, as it stands, takes.
I mean, so just to say,
Right.
suppose you had a correlator within a path integral.
Okay.
I have phi 1 at Z, phi 2 at 0.
Yeah.
Okay? And I want to know what part of that comes from
HK.
HK. So I've got other insertions.
Mm-hmm.
I'd like to know how much of that comes from. So is there some way of knowing?
Without actually doing the.
I mean,
full
of
part
course you can in some.
Right. Right. I'm not aware of that for the most general theories. Maybe for West-Zubino-Witten models, we can just use the Casimir technology to go ahead and do it.
Yeah, it's
Which is
projecting
where-
onto the right block, right, in the end.
Correct. Correct.
So how do you do that projection? Right.
We have to give an ordering to all the representations, I guess, and then figure out where.
Actually, in particular theories, you can use a monodromy condition. Often the monodromy
Mm-hmm.
projects onto a block. Right? Because suppose there's a unique operator of the dimension of HK.
Okay.
Then whatever you have here would have to combine, all the rest would have to combine into the
Correct.
conjugate
Yes.
of it.
Yes.
So it will
Right.
have to have the monodromy of twice.
Of this guy,
Of this
the H. Yeah.
So Maybe
Yes.
not really.
But for example, if we have not a unique operator with the same
If you don't,
conformal
yeah.
range,
Yeah, so then
we, yeah.
Yeah.
Yeah, so perhaps for these Virasoro minimal models and for, say, Witten models, we have more information about what kind of symmetries act on these primaries. So in that case, we can use some additional information which presents themselves as simplifying features only in specific theories. But right now, this is an attempt to figure out the least number of objects that one has to introduce and try to be as economic as possible to see what kind of conformal field theories we can have. So in that spirit, one would like to have the least amount of information as to what this does, except for its transformation properties. This is not my personal point of view or anything, it's just this program by Moore and
No,
Seiberg.
it's very interesting.
But okay, just in simple-minded terms, the intertwiner is what gives you the state you would generate
Right,
by taking the OP and projecting to the right.
right, yes.
So you take any two operators in these states, not just
Any two states?
find the,
Yeah,
and find the operator which will project a particular state in whatever is represented can appear on the right hand side.
yes. And because of the representation theory of the Virasoro algebra, if we do it for primaries, then we can also do it for descendants, because they are just derivatives acting on the primaries. And similarly for the extended objects. So there are some easy parts to this which arise from just taking primaries in this. But first of all, this is not an operator in the usual sense because it takes two states and gives one state. Right. So one would like to then just plug in a state here and call that as an operator. That is the chiral vertex operator. So I would like to start using a pictorial notation because it's intuitive and also easy to write on the board. So I denote this. This should have three legs, two incoming and one outgoing. And I would like to write the one at Z to be on the top, one at 0 to be here, and denote what Z is. And the thing that it projects onto is written here. And to make this into an operator, like I just said, you need we can specify either the state here or the state here. I would like to specify the state here to be some Vi. So given a state Vi in this representation, this acts on a state in Hj to give a state in Hk. So this is like a control state. Okay, and if Nijk is greater than 1, then there are many ways in which Hk can sit inside Hi tensor Hj. So there is also an index which runs over 1 to Nijk, which tells the particular channel in which this K is projected. So I would like to also add that index somewhere here. Okay.
So if you take two states which are primaries,
Yeah.
and then you will always get a primary. Or is that a constraint?
Not really. We can, no, right? Because there is a Z here, so one would usually get primaries and a series of descendants. So just because we are all physicists, we are familiar with 3-point functions and OPEs, and we know how when two primaries combine, we know that there is an infinite tail. So this can be quite abstract, but I guess because we have motivated it from correlators in physics, we can always try to get an intuition as to how these behave from that.
So I didn't understand what the role of Vi is. What is Vi?
That is to make it into an operator acting on the Hilbert space of states. Right? So this takes two states and then gives a third state. An operator acts on one state to give another state. So I just take a state here as a parameter in my operator. So there is an Hi worth of states, operators which act on Hj to give a state in Hk. And they are all indexed by a state in Hi. That's it. Alpha stands for the different number of ways in which pi k sits inside pi I and pi j.
So I was the representation
pi times
and
pi.
Vi was the vector in that representation.
In that representation.
So it could have been not the primary but a descendant.
It could also be a descendant or a linear combination and so on.
Yeah.
So you didn't get what alpha was?
Yeah, sorry. Alpha runs over.
Many copies of HK.
So once I fix ijk, I know this number, and then alpha just goes. Alpha goes over the number of ways in which I can get a state in k.
alpha is not one of the ways? That is, you specify which.
Yeah, so there are nijk ways of.
Oh, right, yeah, you're specifying them.
Correct. So the freedom here is one complex number and a finite number of things and an infinite number of points in this infinite dimensional vector space. Right. Okay. So all the properties that we study next, in particular fusion of representations and so on, should be independent of the particular state we choose here. So that's one thing that we can expect from this.
So HI could be an arbitrary descendant, but 8J you're assuming to be primary, yeah?
Not really.
But then you need a VJ there as well?
No, this is an operator which acts on some state in 8J. So this guy
Oh, it acts on
acts on something in VJ to give something in. Right. So one can also introduce the symbol, which I'm not going to do because it's too hard to have these many notation in just one operator here.
Right.
So it's basically something like this. V alpha, or maybe I'll put alpha. So it starts with takes two representations and projects onto the K representation in channel alpha, controlled by the state V in I. And it's a local operator inserted at Z. Okay, that Z comes from this co-product here.
You're just freezing VI so that it looks like a matrix.
Sorry?
You're just freezing VI so that it looks like a matrix.
Yes, precisely.
The
Yeah.
only reason Simon could write it was he was a
Mhm.
Sort of stripping out all the position dependencies and picking out the numbers which you will just fix by
Yeah.
conformation.
Yes.
And that you are calling that you're creating some sort of a matrix out of that thing. That operator is combination of those numbers.
Yeah. So let me just take a simple example and show what that is. And we'll see that it's just a 3-point function of 3 primaries. So, okay, I think I have to be quick to proceed.
We don't have to finish. Yeah.
Okay.
Yeah, just, it should be.
At least one constraint on these chiral vertex operators is what I'm
Yeah,
trying
it
to
would be nice to get to a result.
Right. Right. Okay, so for example,
Which part is CVO here?
this guy. Okay, let me
You picked up a particular state in HI.
yeah, let me declutter the board a bit. This is useless from now on. Unfortunately, we need this, but I'm going to, so this subscript I tells us that it's a state in HI, okay. Alpha runs over this, I can erase that. So let me write this above. I guess if we do it from scratch, it'll stick better. So I would like to take the tensor product of 2 representations, one at Z and one at 0. So I'll put the Z equal to 0 guy here, and I'll put the one at Z here. And there are n ijk channels indexed by this letter alpha. And I would like to get a state in K, so I put the label K there. So this is like some kind of a transistor, if you wish. There is a control parameter here, kind of a voltage. There is something you send in here, and you get some output here. All right.
So you have to choose the state VI.
Yes, that's like voltage. Without voltage, you don't see a current. I guess. So
Can you think of this as a generalization of what you usually would say as test coordinate input?
yeah,
Generalizing that to.
it's precisely that. It's precisely that. In Klebs-Gordon, if we have say J1, M1, J2, M2, right? So we would like to form an operator which projects onto one of the direct representations in the direct sum. So we form this operator and then do, right? There are some more indices here. Basically, this is the point. Right? And it has to be summed over all M1, M2, and so I have capital J, small j1, small j2, that's these 3. For SU2, the fusion coefficients are usually 1 or 0, so we won't see that additional complication here. But it's precisely this for finite dimensional groups, which I have written there.
And you sort of broken the symmetry between I and j because one of them is at 0 and the other one's at z.
Yeah. So that's actually an important point. Here, this again, as we can see, even if we put a zeta here, this expression is not symmetric in zeta and z. Even if we have two general dependencies, because of radial ordering in the way we did it, where we could compute it in the opposite radial ordering and we'll get another expression, and though that expression will not match this expression, but its action on the states of the algebra will be the same inside correlation functions and so on. So we don't expect these two operators to match at the level of operators in the algebra or in the tensor product of two algebras.
You're saying that the expression won't match even if I write it in the other patch, or
Other patch? You mean the mod z1 less than mod z2? I'm talking about the different radial orderings. Patch is fine. It's just one of those global conformal transformations which you can do on this. I'm talking about z1 greater than z2 and z1 less than z2. The expressions for the two radial orderings will differ.
So, sorry, within the path integral, if I put one at z by 2, the other at minus z by 2.
Okay.
Then I get and I do the OP around the origin. I expand around the origin. I should get something that's looking symmetric. I presume you will, however you will.
Okay. So if I say this is z and this is minus z, for example.
Yeah, I put one operator at z by 2, the other at minus z by 2.
Then there could be a symmetry, yes.
Yeah.
I guess you can see that once you also include the other part here, right? But they are at the same radius, so that might be problematic. I'm not sure. Yeah.
In the case that Chiral was saying, I would think the L should just add, right? If you have at Z, because it's like it's like having two different operators which are space-like separated.
Correct.
And then the representation should just add, right? They should not.
What
No.
do you mean add?
They should not have any OPE or anything, right? They just commute. They're space-like.
Suppose we're just doing Euclidean space. It's just a translation of what he's doing.
Right.
So it's just that I'm expanding the operators not about one of the positions of one of the operators or the other one, but about the midpoint
Midpoint.
to make it more symmetric. I think the general properties will not change very much.
But I guess if one does not go through this business of co-product and so on and just take 1 plus ln 1 times ln plus ln times 1, I think what Loga is saying is that itself suffices for this particular case.
But then what about your problem with the central charges?
I think what he's claiming is that there will be no issue with the central charges in that case.
How can that?
I don't
how
see
can
that.
Be? I thought you had a general.
Yeah, it's just simple addition.
Yeah, it can't be, right? I mean, as you said.
Right. All right. So let me also write this control state here. Okay. So this takes a state in Hj to give a state in Hk. Okay. Now, what I would like to do is consider correlation functions of these chiral vertex operators. So this is the next step where I have intertwiners between these guys. And I would like to see what happens if I have 4 representations or 5 representations and so on, and how it decomposes in terms of these 3-point functions. So it's just increasing the complexity one by one. So first we listed the number of the representations that we want in our state space, and then we saw how they tensor and then decompose into other irreducible representations. Now we would like to consider tensor product of 3 representations or n representations, and then see how much of that information we can capture by studying these 3-point functions. From the physics side, we know the answer that 3-point functions are sufficient along with other data to decide the rest of the set of correlation functions. And we would like to recover something similar here, because after all we are trying to describe physics through a program where we are trying to classify what all possible conformal field theories can exist.
Fuse one pair, then fuse the result with another operator.
Right, and that will give us constraints on the correlators.
Yeah, exactly. That would be one.
But just a little confused. I mean, I was thinking of this chiral vertex operator as a map from one Hilbert space to another.
Mm-hmm.
But you're saying actually you can also think of them as just operators in the, at least the chiral CF, is it?
Yes,
Yeah.
which have support only on HJ.
Which have
Support only on HJ. So they're quite singular operators because we can't expect them, if we have a huge infinite dimensional matrix, we can't expect them to behave well under block diagonalization, for example.
Can't I think of it just this way, that if I have operator 1 at Z, operator 2 at 0.
Right?
The chiral vertex operator is the part of the OP
Yes.
that gets contributions from HJ and its descendants. The operators at J and its descendants at 0.
At 0. And also the projection onto HK. So we are looking at that part of
Yeah,
the
only
answer
the part.
which has
Yeah. So
HK.
suppose I take a full correlator.
Right.
It's only the part that comes from J and 0 going to K and
Correct.
its descendants.
Correct. Yes.
So the 2-point function of this beast is related to the 4-point.
If
Right.
you take 4 of them,
Precisely.
you fuse these two, you take the 2-point function.
Precisely. Yeah. Before I proceed, let me give an example of that where I take Vi to be a primary and I act on the primary state in Hj and project onto the primary state in Hk. Okay, which is basically sandwiching this between Bj and Bk. Well, Hj and Hk. Okay, so then this we can see will be something like a number, which I'll call asCijk. These are primaries times Z to the, okay, let's see. So this is HK.
In general, there will also be an alpha dependence.
Yes, yes. So these are the 3-point, these are our good old 3-point functions between primaries. If we take a descendant here, for example, we'll have a tail. If we take a descendant here, we'll have a tail. But this captures the representation theory part of it. So in fact, this was one of the initial attempts to define these chiral vertex
So
operators.
you've chosen all three to be
Primaries.
primaries.
Yeah, so this is also a state. Yeah. So when Moore and Seiberg started doing this, they did not have a definition of the chiral vertex operator in terms of the coproduct and so on. They constructed it by hand for most of the known rational conformal field theories by studying the 3-point functions and by using the fact that this will also decide descendants and so on.
Alphas would basically parameterize all the CIJ case you have.
Yes,
Possible
the space of Cij case you have. Bootstrap, the usual conformal bootstrap constrains these. So this is some kind of a holomorphic version of that which does not determine physical data yet. It just tells us how these objects behave under conformal transformations. Recall that all this business was started because we had an infinite dimensional algebra and central extension. Right? That was the reason why we needed to have a Z, and this naturally gives rise to a vertex operator in the theory as well. All right. And similarly, if I take J to be the vacuum representation, then it's easy to see that this will be non-zero only when I is equal to K. And conjugates of that. All right. Right. So one can also obtain the position dependence of this operator by using L minus 1 acting on HI or VI. We know L minus 1 acting on the state corresponds to d by dz acting on, so L minus 1 acting on VI. This is the same as d by dz acting on the original operator, and we can solve this. If we know how this chiral vertex operator looks like, can solve this first order equation to get the position dependence of this guy. So really the representation theoretic content is contained not the Z dependence as such, that is completely determined by the conformal algebra, but in how these things fuse. All right. This Z goes along for the ride and so on. So let's consider correlation functions of chiral vertex operators, and those are called the conformal blocks. So we just combine these in the appropriate way possible. So since this is projected to a state in HK, whatever we append to this should also have input in that particular space. So I can consider a correlation function of two chiral vertex operators at Z1 and Z2, starting with let's say L, fusing with K at Z2 in channel alpha 2 to give a state in HP, and that P fusing with J in channel alpha 1 and then giving a state in I. So this is an operator, and I can study its correlation function.
Alpha 1 and alpha 2 has to be the same, right?
Not really. This is a channel for this fusion. This is a channel for this fusion.
Which copy?
Which copy of the representation?
But I'm confused because here, one of the two is always at 0.
Oh,
And
correct.
I
So
thought
L
when
would be
the
at 0.
right was at 0.
So this would be at 0.
But now that's not at 0 anymore. Oh, it was at 0 because you took the OP and expanded around 0. Thank you.
Yes, precisely. So you're saying how can we combine this if this is not at
0?
yeah,
But
right.
it was, yeah.
Okay. Let me put this here. So I have to take a state in HL and a state in HI and study how this looks like. So this is called a holomorphic conformal block. Let's see what data it depends on.
But I actually am still confused. I thought that would output a state at 0. Suppose I took the left prong.
This guy. Oh, here.
I thought the output of this was a state at 0. For an operator at 0.
No.
You're saying it's just a state?
It's just a state.
Just a state, and then
Yeah.
I translate it. In operator language, I'll translate it to wherever.
To wherever you want, yeah. Using e to the L0.
Fine.
Yeah. So this depends on these
There's a
spaces.
Z-dependent propagator sitting there
In P, yeah.
yeah. So non-trivial Z-dependence in the P line.
In the P line, precisely. So, and then this depends, of course, on the locations of 4 operators, one of which is at 0 and the other at infinity.
Right.
Okay. So there are 2.
Actually, 0 was never very important. I could have just done Z1 and Z2.
Z2. Then this would be Z1 up to Z4.
Yeah.
Using conformal invariance, we can fix 3 of them. And then this also depends on the channel P, not channel, channel representation P in that channel, and also the fusion channels here.
So far, this looks like the Levin Collet going down.
Yes, but they did it for the physical correlators, which had this and its anti-holomorphic counterpart combined in a particular way.
But still, it just seems like
It's the same idea. It's the same idea. Okay. So one can consider endpoint conformal blocks just by taking this.
And there are many different ways to do the fusing now.
Right. Now we can count because we know what alpha 1 and alpha 2 run over. And we know how many p's exist. So the dimension of the space of this guy would just be, okay, first of all, let me call the space of these chiral vertex operators to be V, I, J, K. Then this sits in the space V, I, let me be careful, V, J, P, giving I, tensor V, P, K, L. Okay, a P. Sorry. Right? And the dimension of the space is just
Which one are you putting up and which one down?
up is the resulting space. The ones down are the ones that are fusing.
So then I didn't understand why.
So KL first fused to give P, and then JP fused to give I.
Oh, you get JP fused. I see.
Right. And then I sum over P to talk about all possible
The
representations.
way I normally think of the OP, though it's probably equivalent, is I fuse these two and I fuse these two and then
Yes.
I suppose that's equal.
No, that depends on where Z1 and Z2 are in this particular picture. So if Z2 is close to 0 and Z1 is close to infinity, that's precisely what is happening. Okay. So this is the dimension of the space of 4-point conformal blocks. All right. So now comes the interesting thing, which is let's try to upset the ordering of this by taking the operator at Z1 to Z2 and the operator at Z2 to Z1. Okay, but before this, any questions at this stage?
What was the dimensionality of?
Of the space of 4-point conformal blocks. I don't know, cook up some symbol for that, I guess.
The number of
You just counting the composite index alpha 1, alpha 2.
Right.
No, with P, summed over all P.
It's also summed over all P. Yeah. Given a particular P I know what alpha 1 and alpha 2 are, and I'm just summing over all those numbers.
Now the way you're doing it is you're taking two guys fusing
Right?
to get a whatever chiral vertex operator. What's
Yes,
that?
chiral
That's
vertex operator.
Then you take another guy and fuse with that chiral vertex operator.
Yes.
And
Then
then you
get-
find you want to get your fourth guy.
Yes.
The
Yes.
result of that is your fourth guy.
Right. There are many ways of doing that.
Yeah, I know.
Right.
It's just not the way we, at least I know.
No, that
Yeah.
can be. So there are different corners in this
Yeah,
space of Z1, Z2.
Yeah.
A moduli space of insertions on the sphere, to be technical.
Yeah.
Where if I bring Z1 and Z2 close, then I have to fuse J and K first.
Yeah.
And then I and L will get fused. That's in fact one of the identities, one of the duality moves. The other one is, like I just said, taking J across K, interchanging the locations of these two, and so on. Okay, so we can do this for n-point blocks, and it's very simple. Let me erase this part. But before that, we have to be careful in defining branch cuts, like Gautam was pointing out at the beginning of the talk, because these are just chiral halves of the conformal field theory. So the full physical correlator should be invariant under these interchanges from the path integral point of view. They should not pick up phases, and there should be no the physical correlator should not see the branch cuts, but physical correlators are sums of linear combinations of holomorphic block times an anti-holomorphic block. And there, each of the pieces can carry a monodromy as you change the locations, such that the two monodromies cancel at the end. So this is kind of in the same lines as when I have a primary of the full conformal field theory, it has a holomorphic part and an anti-holomorphic part. And the fact that this full guy should either behave as a boson or fermion in 2 dimensions constrains the conformal dimensions of these guys. So h minus h bar of that primary should be a half integer. But h and h bar itself can be whatever number, consistent with the other requirements in the theory. It's kind of the same statement applied to this. So this can have weird behavior as we go in the moduli space of locations. But eventually, these have to be combined with their anti-holomorphic counterparts such that those don't appear in the final answer. So as we can see, we now do have some freedom in choosing what we want for the holomorphic half. And Moore and Seiberg's program is to see whether we can completely classify this. Okay.
Completely classify
Which kinds of
can appear.
which kinds of ends can appear and what representations can appear, which central charges. So in that sense, it is a continuation of BPZ, where they discovered the minimal models by following precisely that prescription, but for physical correlation functions. All right.
So if I want to define a C equal to 1 theory
Mhm.
with C bar equal to 0, that
Uh-huh.
is to say it's a chiral boson,
Right.
then this is the kind of stuff I will encounter.
Precisely. Yeah. We know examples of that, which is U1 Bezumanov-Witten at a rational level. I mean, a rational torus, which means U1 at an integer level. and just take one copy of that. In fact, that is quite relevant in the condensed matter context, where they use the conformal blocks of that theory to describe ground states of fractional quantum Hall effect and excitations and so on. So the chiral halves are not completely physically irrelevant because the lowest lambda level in the quantum Hall effect is usually described by the holomorphic wave functions up to a normalization factor, which arises due to coupling of the magnetic field. But that holomorphic part should capture the fractional statistics of the excitations about the ground state, and these are precisely the candidates for that.
But if it's just holomorphic, then do you have single valued correlation functions?
Here we live in the multi-valued.
What I'm saying, in a physical situation, if just the chiral theory is the whole theory,
Then we have to be careful. Yeah. We have to
maybe
make sure.
because it's a wave. The map is that this is a wave function, perhaps.
In the physical theory, yes,
Yeah.
yes, precisely.
So then
But
you
it's a
live
wave
in-
function for anyons?
Wave function, so in fractional quantum Hall effect, the fundamental particles in that phase are anyons. So we can also write down a wave function for electrons by considering
I understand.
n
But
anyons. And
if
that's
you just look at the wave function for anyons, you expect monodromy.
monodromies, yeah.
So that you live with it,
Yeah.
that reason, but also that it's a wave function, so it need not be single value.
Single value. It's psi bar psi which has to be single valued
And in fact,
again.
the non-single valuedness is basically the statistics. Isn't it?
Right. In that case, that's essential for the physics.
But I mean, if it was a field theory, then, and these were really correlations, then you couldn't live
No,
with it, right?
No,
So, okay, the chiral blocks become physical because they map to.
precisely.
Yeah.
And one should also remember that the fractional quantum Hall effect is in 2+1 dimensions, whereas these are in 2 Euclidean dimensions or 1+1 dimensions. So the correlators of the fractional quantum Hall effect, or the wave functions of the quantum Hall effect, can be described on a time slice, and there it can have funny business happening, which is precisely this. That's also the story which Witten discovered in his paper on knots. And the connection to fractional quantum Hall effect is that people in the 90s, Shucheng Zhang, Kibelson and Hansen, they figured out that the low energy effective theory for the fractional quantum Hall effect in terms of electrons is very hard to write because they are strongly correlated, but it can be written in terms of anyons as the fundamental objects. And the action for that is precisely the Chern-Simons action at a particular level that depends on the filling fraction, coupled to a boson or a fermion. So then the excitations of the boson field or the fermion field will carry fractional statistics because of the non-zero level of the Chern-Simons theory. And Chern-Simons we know corresponds to the Zumano-Witten on a time slice. So wave functions of ground state wave functions of that emergent theory can be described in terms of space of conformal blocks. Okay, so let me quickly talk about the branch cuts, because that's going to be essential for defining the first duality move. So if we have this this situation where we have 2 chiral vertex operators, then we have to choose branch cuts to allow for monodromies. So in the Z plane where I have inserted operators Z1 and Z2, I choose my branch cuts to be along this, and along this negative real axis. So whatever moves I make, I can make, I should make without crossing the branch cuts of these guys. So that kind of, if I want to interchange Z1 and Z2, it gives me an orientation in which I do it once I choose the branch cuts. So if I am in the regime where Z1 is greater than Z2, which is this case, then the way to perform that move where I interchange Z1 and Z2, the operators at Z1 and Z2, is to take different color, like this. All right. And now we know that.
I'm sorry, what was this? I saw the. Yeah,
So it's taking the operator at Z1 and putting it at Z2,
it's Z2.
and taking the operator at Z2, putting it at Z1.
And what is this? The
So-
initial locations are the mod Z1.
Yeah. Yeah. So in my conventions, I choose Z1 and Z2 to be fixed points,
Okay.
and locations to the operators are. So this is always satisfied.
Got
All
it.
right.
Okay.
Okay.
So you're looking at the nature of the function, this FIJK is
How it changes when I
so it's a function
interchange
of two
Yankee.
complex variables,
Right.
Z1 and Z2.
right? I can do many things, which is take Z2 around the origin. That will certainly pick up a phase. Or Z1 around the origin. But I am interested in this where Z1, Z minus Z2 goes to Z2 minus
And
Z1.
these are the two, these two operators are the same.
Not necessarily.
One and two.
Not necessarily.
Not necessarily.
That will give some insight into mutual statistics and so on. But as far as this is concerned, it will have its own.
But then you're going to a completely different situation. It's not back to the same law.
Sure, but it has the same four, from the path integral point of view, it has the same four insertions in the path integral,
Though at different locations.
though at different locations. So the hope is that they might be related to each other,
Yeah.
not
But
the
if
same.
they were equal, then you'd have to get a linear combination of the blocks, right?
No, even otherwise,
What?
even otherwise,
Oh, because the blocks depend on Z1 and Z2.
precisely, yeah. Okay, so this definition requires that Z1 minus Z2 not belong to the set of negative real numbers. So that's the statement that they should not cross their branch cuts when we try to analytically continue the locations of the operators. When I interchange the locations of the operators and I look at the conformal block IKJL, where J is now at Z, K is at Z1, J is at Z2, then this is defined when Z2 minus Z1 is not a negative real number according to this prescription. So the common domain of definition, we have to first, to compare two objects, we have to make sure that they are defined, well defined for fixed values of Z1 and Z2. So we see that in the Z1, Z2 plane, one of them is defined in the region where this is cut out. The other one is defined where this is cut out. So the common domain of definition becomes disconnected in the upper half plane and the lower half plane of Z12, which is Z1 minus Z2. Now the claim or the restriction that one would like to impose a la Moore and Seiberg is that as long as they are in one part or the other part, the linear combination that relates this to this does not depend on the actual values of Z1 and Z2. But let me write down the claim so that it's easier to follow. So the claim is that this block, which has I, J, K, L at Z1, Z2, I omit, let me write P, alpha and alpha 2 are suppressed. This should be a linear combination of Z1, Z2, but with K and J, I and L, with a matrix here. Let me write the matrix on the right hand side. So the matrix should depend on, so this is the braiding matrix or half braid matrix. The claim by Moore and Seiberg is that it should depend on P, depend on Q, with Q being summed over. Of course, it has to depend on the particular representations we choose, and this is the notation for that. You choose an ordering around this diagram and then write this for the same. So this is the braiding matrix for this conformal block.
The eigenvalues of this have to be square, have to square to e to the power 2 pi I.
The conformal dimensions. Yes. If we choose, so this is an operator, right?
So this is why
If we
it's
choose
equal,
primaries.
because it's like a square root of going around.
Going around, yes.
Which we know.
Which, yes, precisely. So the eigenvalues should be that. So this also depends, let me write down alpha 1 and alpha 2, beta 1, beta 2. Oh, I just have 6 minutes, all right. So,
As Sandeep said, we can continue on, let's say, Thursday.
okay, but I would like to get to
get to
one thing, yeah. So these are the things that this depends on, and also, like I just said, the common domain of definition of these, of the left-hand side and the right-hand side is disconnected. So in principle, the matrices for those two domains of Z1 and Z2 might be different.
That one by
So epsilon is a sign, So first of all, let's study this. So given a channel, a representation in the channel, that's P, I have to sum over all the blocks with Q there. So that's this. So this is a matrix in this PQ space and also in the channels. So the composite channel is indexed by alpha 1 and alpha 2. Here it's beta 1 and beta 2. So this is a huge matrix with 3 indices, say P alpha 1 alpha 2 going to Q beta 1 beta 2. And the domain of definition for Z1 minus Z2, so this is the origin of Z1 minus Z2, is split into 2 parts. Imaginary part of Z1 to positive and negative here, maintaining this, maintaining the ordering. All right.
Sorry, I'm really confused about something. On the left-hand side, you inserted the K operator at Z2
Yes.
and the J operator at Z1.
Right.
All said and done, on the right-hand side, you're inserting the K operator at Z1 and the J at Z2.
Yes.
right?
Yes.
These can be very different operators. Why
Right.
why is the answer on the left-hand side? You're saying just
Okay.
from continuation, I go from one to the other, so it should be some phase or something.
Something. But let me give you a more concrete understanding of this.
Like if each was solving some hypergeometric equation,
Precisely,
all
yeah.
right, fine, that I understand.
Right.
in
But
general,
in
it
this
doesn't-
situation, let's say we take one of the Virasoro minimal models. Usually, when in rational conformal field theories, there are null vectors. So we can insert the states corresponding to the null vectors here, and then these correlators will solve a differential equation corresponding to the level of the null vector. And the space of such things will form a fundamental system for the differential equation. And these also solve the same differential equation because it's the same operator that's being inserted.
It's a finite dimensional.
And it's finite dimensional because that's our assumption at the beginning. So then they have to be related by a basis change.
But maybe I can ask Sandeep's question again. If after you do your sum on the right hand side, don't you have to set Z1 equals Z2 and Z2 equals Z1? If it's going to be the left hand side.
Oh, that's so.
No.
It doesn't seem so.
How can it be otherwise? Because you have to have the same operators inserted at the same point.
Not really. I mean, this is a correlation function that depends on Z1 and Z2 once I insert states. And this is another correlation function that depends on Z1 and Z2.
Z1 and Z2. But so as a function of the locations of the operators,
Okay.
you get linear combinations. But
Yes.
surely you're not going to evaluate these two functions at different points.
I think he's
Well,
you evaluated it.
That is not.
No, I evaluate them at.
You go from one to the other smoothly, and it keeps solving the same equation. You come
But if the two operators have the same properties or something, then I could believe that. But one has dimension delta 1, the other is delta
Right.
2.
Okay.
It's just totally different if delta 1's at this point and delta
That's
2's
what
at
I was asking. It seemed a
I
lot
can't
to me.
believe this. I can't believe
Let's
it.
see. K is the way it's written. K is at Z1 and J is at Z2 here, with
Yeah, maybe some.
Z1 and Z2 being fixed in the complex plane.
Like if it's the solution to the same.
Yeah, he's got some vector in a Hilbert space. The way he does it, there's some vector in a Hilbert space. But what is this saying about the blocks themselves? The blocks, let's say, are functions of the positions Z1, Z2, Z3, Z4.
Yes.
Now, forgetting about all subtleties, if 1 and 2 are different operators,
Okay.
you interchange them, there'll be no relationship between the two
Well, that's
functions.
what I was saying. Yeah.
Sure.
Just because it solves this hyper. Go ahead.
No, I mean, one of them has they're different dimensions, so they're different, like the monodromy of one around the other
Right.
will be just totally different.
No, but as long as we just interchange Z1 and Z2, somehow I feel that.
No, suppose I look at the monodromy of 1 against 3.
Okay.
If you interchange Z1 and Z2, the eigenvalue space of possible monodromies
Okay.
is different. Right? Because in one case it's the OP of, so that sounds, I mean, I think what you must
I
be
guess
saying,
a better way of putting this, though I don't know how to do that here, is to say that I take Z1 one full round around Z2. This
that
is some kind of a square root of that.
is symmetry.
Yeah, this is a square root of that. So I'm certainly changing the locations of the operators.
Exactly. I think what you are doing is relating what you get to the analytic
of
the
the other
original
one,
block
right?
after flipping Z1 and Z2. I mean, you know the way
The
you say
analytic-
that the vector of a Hilbert space, I don't know how to say it. But if you
Sure,
just think
but-
of it just
yeah.
as a function of Z1, Z2, Z3,
Mhm.
Z4. It's just impossible.
One of them is an analytic continuation of the other.
Exactly.
Yes, precisely.
Exactly.
Yeah.
Yeah,
Okay.
one of them is, but what exactly is the analytic?
The analytic continuation where you think of it as a function of 4 variables
Yes.
on the left hand side, let's say, and in the slot of the first variable you insert Z2, and the slot of the second variable you insert Z1.
Okay, but then in effect, haven't you made, if in the, that slotting is that whatever is going into, what did you call it, the first slot is the, I mean, in effect, haven't you put the, in one case K at Z2 and the other case J at Z2?
But the point is that the space of conformal blocks is not one dimension. So in doing that, in actually going around or just taking the analytic continuation, you might be getting a linear combination.
Yeah, I mean, for example, here, if we start with imaginary part Z1 to greater than 0, when we do this half braid, this will split sign because Z1 and Z2 are being interchanged. So they are not in the same domain of definition then. So I have to analytically continue one of these back to the original domain of definition, then compare them. So the correlation function which I get by just naively putting these two in the mutual locations here, we get a correlation function which is well defined only for the location of this operator now being radius of this operator being greater than the radius of that operator, which is in a different region in Z1 and Z2 space. But I have to bring it back to the same region by avoiding the branch cuts and then compare the
That's
two.
what you're saying.
Yes.
Now I begin, okay.
Right.
Right. So it's actually that, now
Right.
analytically continued.
Precisely. Yeah.
Yeah,
And
now it makes sense.
Yeah.
Okay, now it's got a chance to.
to
Sorry,
be
I
to be
didn't-
linear combinations of each other. But the point here is that
It couldn't have worked, yeah.
It just,
right.
yeah.
But these two domains are different. So this braiding matrix can be different if we start with Z1, Z2, imaginary part positive or negative. But it's easier to see once we assume that this B is independent of Z1 and Z2, as long as they're in one of the upper or half or the lower half, that it just depends on the orientation of the interchange. Like I said, when I had the two operators, the interchange was, let's say, clockwise in one prescription where the imaginary part of Z1 and Z2 was positive. The other guy would just be the opposite move, the exact opposite move, because the branch cuts were like this. So if I had Z1, for example, below Z2, which would correspond to this case, and the branch cuts are of this kind.
I thought you were choosing all the branch cuts in one way.
No. The Z1 minus Z2 has this branch cut, which means that so they have the branch cuts run in the opposite directions. So here to avoid branch cuts, I have to go clockwise. Here to avoid the branch cuts, I have to go counterclockwise. So it's basically the opposite move to what was happening here. As long as the braiding matrix is independent of the locations, one is the inverse of the other. So for epsilon plus, which corresponds to this domain of definition, whatever braiding matrix we get is the inverse of the braiding matrix we get for epsilon minus. So that's one thing which, there are two braiding matrices, but one of them is the inverse of the other, as is clear once we include the branch cuts into consideration. Okay, let me just quickly give.
So just to let me try to fully understand that. Okay, you compute firstly the blocks with some, because in general the blocks are multi-valued functions.
Yes.
So you have to choose your branch cuts.
Yes.
So you do that and you compute this block, which is totally well specified.
Right.
On the left-hand side.
Yeah, including radial ordering also. So
Including radial ordering because Z2 and Z1 are given.
precisely. Yeah.
And,
So it's in one region of Z1, Z2 space,
in one region, no?
which has to be analytically continued by avoiding the branch cuts.
Okay, so
Right.
you choose that.
Yes.
Then what you do is
Mhm.
that you compute, you exchange, so to say, the locations of J and K.
Mm-hmm.
But now you say they are at different points.
Right.
Now you
Yes.
And k to the point z2. Even here, having exchanged them, now you, to do that,
So we look at the form of the answer
you look at the form of the answer.
and see that it can be analytically continued as long as it doesn't cross the branch cuts.
So you do that continuation, and then you
Bring it to the same region of original definition of these, and then do the comparison.
Okay, very good. So I'm sorry, just to be dumb, you take your diagram, you first have j at z1
Yes.
and k at z2.
Yes.
That is this one.
Yeah.
Then what you do is, to do this, you actually first compute with j at z2 and k at z1.
Yeah.
Okay, and then avoiding your branch cuts carefully, you do a move to bring it back.
Yeah.
And when you do that, and you sum over all the channels with this matrix, you get back the origin.
Yeah, and when you do the second, you've not gone back to the first, because the branch cuts have not come back to where they were.
Right.
Let me just understand that. So you did that,
Right.
you chosen the branch cuts the way you did.
Yes.
And
So now this is the initial configuration.
Can you just write?
So the final configuration is the branch cut is here, and the other branch cut is here. So it's two operators, but with the branch cuts in the opposite directions.
Because he started this way and then he's gone like that.
Right.
So this has come here and that has gone there.
Right.
Sorry, I'm sorry to interrupt your seminar, but I mean, so you start with, here I would have said k
Right.
and j.
Yes.
Then what you do is, here to begin with, you just take this calculation,
I should
and
change
I
the
would have
labels.
said you made your choice of branch cuts like that,
Right.
but what you do is, you take k at z2, so you take j and k at z1 and z2.
Yes. Precisely.
That's this calculation.
Precisely.
But now, and I thought your choice of branch cuts is this.
No, the branch cut goes along with the operator.
Oh, the branch cut goes along with the
So it's
operator,
like a
right?
tail.
In the continuous motion.
Right. I mean, the branch cut is part of the operator. The operator being multi-valued is not precisely local. It has a Dirac string which
Oh,
goes
I
up
see.
to
Okay,
infinity.
that's what I wasn't understanding.
Right.
Okay. So you say, no, here the branch cut is like that.
Yes.
Here it's like that.
Yeah.
Okay, now I understand. And now you want to go back to the situation, so you go back here and you go back here. Which with your branch cut can you do or not do? If you just tell me. I mean,
We can
which
do
way are
that.
you supposed to do?
We have to reverse our thing.
Yeah, Naveen, maybe I can say it one way and you tell me if you think.
Okay.
If you continuously take 1 to 2 and 2 to 1,
Okay.
you change the position of branch cuts compared to what you naively have had.
Correct.
And then you re-express this object in terms of the object with the naive branch cuts,
With the original branch.
with the original branch cuts.
Correct.
And that is your matrix. This re-expression is your matrix.
That is one interpretation of what is happening.
That's basically what's going on. Do you see what I mean, Naveen? Yeah. That his rule was that this guy should have had a branch cut this way. This guy should have had a branch cut this way.
Okay, this makes sense.
Okay? But when he does the reversal, he's not got the right branch cut structure. Okay? Then you re-express that in terms of the right branch cut structure, and that's your.
Okay, that's some analog of active versus passive with him, because he's associating his branch cuts with the operators.
Right. Even here,
In which case, once you move your operator up, you will automatically have the right branch cut structure.
no, we are not moving the operators up.
When you
We are,
move these branch cuts here, you're not have the right structure.
that it
Because
becomes
you have
this.
to move with the branch cuts.
So it's still active, the active picture where the branch cut moves with the operator. But the thing is, this is not my prescription for a conformal block. My conformal block prescription has branch cuts in the opposite orientation.
Exactly.
So I can take this new block and then re-express it in terms of my old blocks, which have the correct branch cut structure.
It's like you've gone out of your gauge. You have to re-gauge structure.
Precisely. So it's like moving the Dirac string around.
Yeah.
Except that we are not moving the Dirac string, we are just re-expressing this answer in terms of the other answer which we already know by this
So let's
linear
this.
combination.
Your definition of the conformal block is such that let's suppose for a moment Z2, mod Z2 was less than mod Z1.
Okay.
So they're radially ordered.
Mhm.
Then let's say your prescription is that for the earlier Z, that
Yeah.
is Z2, it
Mhm.
goes one way,
Exactly.
Yes.
and for the later it goes the other way.
Exactly.
Let's say that's the one, right?
Yeah.
Now you're saying with that choice, if you
Mhm.
define your blocks here,
Right.
and you go back, you
Right.
won't go back.
Yeah.
We won't go back to
Now
that.
continuously where you break that. So you have to undo that. And that undoing process is these.
We don't physically undo it because
Yeah.
we want to compare things at different locations. But then we can always re-express this solution of the differential equation in terms of
Yeah.
a bunch of solutions with the other branch cut structure.
Locally as functions, you don't care about the branch cut.
Precisely, yeah.
So it has locally as functions, it has to be a linear combination.
Combination of different branch cuts and so on.
The other branch.
Yeah, like Shira said, it's like a gauge choice. Different gauge choices do not change the
No, I'm just trying
the
to
vector
understand
space of
precisely
the
how
blocks.
you're choosing your gauge. That's all. Because
I
So
fix
what
a gauge and try to
precisely-
bring everything back to that
because
gauge
your
once I.
matrix will depend on that, right?
Yes, that's this dependence.
So how exact, just to understand, I
Uh-huh.
know it doesn't matter, but just one concrete exact choice is what? You couple the choice. Why couldn't I just have chosen the branch cuts to always run along the negative y-axis?
Then we cannot do the braid.
You always go through.
We always cross.
You always cross.
So they're careful to choose it so
Yeah,
that you can.
Z1 minus Z2 has to be in.
I see, if you start with it little above, maybe
You'll have to.
you have to do that.
Right.
So it's like that, you start little below and little above.
Yeah. If both branch cuts are going this way, you try to interchange them. You go through.
For example, we cannot take, if we take this around the origin, for example, the branch cuts will cross. Or this will cross the branch cut associated with the origin. So it will always pick up a phase. It will always go to a different sheet as is required by its multivaluedness. But these correlation functions themselves can be consistently defined once we choose the branch cuts. And when we do the braiding, we would like to keep the same convention. Right, so let me just give one identity. Okay, so there is a choice in the next minus 5 minutes I have, which is to show another duality move or give an identity for this duality move.
Let's
which
see the identity. Let's see an
Okay.
output.
Yeah, people might be disappointed with the identity here because it's the Young-Baxter equation.
I don't think we'll do this.
Okay. All right. Okay, so it's very simple now. So once this mechanism is understood, so first of all, let me just make one statement, which is one can. So we saw that the space of these 4-point conformal blocks was the sum over P of V. What was that? P J I V P K L. So we can we can piece together the various B's for different PQs and make it into a huge matrix which has only these indices corresponding to indices here. So B I J K L is a matrix which acts on this finite dimensional vector space to give something in the J and K interchanged.
Sorry, I've forgotten, what was your VJP?
So V was the space of the 3-point functions with what was the J, K, I, alpha. So alpha is the basis, runs over the basis vectors for V, I, J, K. So this was the space of possible 3-point chiral vertex operators with this freedom alpha here.
Is this a number? What
Alpha runs over, if you remember,
Alpha, I know.
Uh-huh.
But if I input I, J, and K, what is V?
it's a vector space
It's a vector.
of dimension Nijk. So what I have done is just put together BPQ as various blocks, and I get a huge matrix acting on alpha 1, alpha 2, and beta 1, beta, the composite channel index. That is nothing but V. What is this? Q, J, L. So now it cares only about the fusion properties of the various representations. It is summed over the different representations that can go in the channel. So that is this sum. That's essentially what we finally want, right? We want to figure out whether the fusion rules are consistent with whatever constraints we are going to write down.
I'm a little confused, I'm sorry. Originally the triangle, this
Mhm.
object was a map from a Hilbert space to a Hilbert space.
Correct.
Now it's a...
The map itself is indexed by a vector space.
Yes, I
Mhm.
understand. So J, let's say, is the index.
Oh, no, no, no. Alpha is the index.
Well,
His vector space is which choice?
no,
That's
no,
what
but
he's
to begin with, the way you defined it,
Right.
after you had this object and
Mhm.
you chose some operator there, and then it was a
Right.
map from one Hilbert space to another, right?
Yes. So here I chose, was that orientation
Now,
correct?
now
Yeah.
you're making the whole thing into a vector, so I'm just trying to understand.
No. So I have an operator here given a choice of V. So this
Yes.
freedom is present.
Yes.
I'm going to forget that freedom for the moment.
Okay.
Assume it's there because that's what makes this into a usual operator, which acts on something, maybe a, Yeah.
Let me call that thing a 2,1 tensor. This
Okay.
object is like a 2,1 tensor, and the space of those tensors itself is a vector space.
is a vector space.
And the dimension of that is given by the basis vectors of that, the tensors is given by that alpha thing.
So basically I have J and K which fuse to give I. Maybe I wrote the order differently
What
earlier.
is the field on which this vector space is valid? I add two elements of the vectors with what? Real numbers, complex numbers?
Complex numbers.
You haven't defined the vector field for me at all.
So it's
what-
complex numbers.
All right.
Let me explain. So I have this. So this is part of this representation Hj. It's like control state, which it's there, but I'm not going to think about it. That's an infinite dimensional freedom I have in choosing the operator. But once I fix this, I have an operator which takes a state here to a state here. But now there is not just one channel in which J and K fuse to give I.
agree. Yeah, you're alpha.
So there's alpha. So I can construct a linear combination of two operators of this kind where I have C1 alpha 1 J K I Bj plus C2 alpha 2, all right, for fixed values of alpha, specific values of alpha 1 and alpha 2. This is also an operator which takes a state in Hk to give a state in Hi.
Okay.
And this is in fact a sum over alpha case, no, okay,
Okay.
alpha m's,
That's the sense in which you have a vector space.
precisely.
Okay. I understand. Thank you.
Yeah.
Okay.
So this is the space of channels.
Okay.
And that is eventually what we are interested in because we would like to constrain the fusion rules. So it makes sense to sum over the various representations that go in this channel. And I
here
have
you're
them.
taking a tensor product of that two
Yeah.
vector spaces.
Because I'm
Then
combining,
tensor product V, huh?
right, yeah, precisely. Because I'm taking two of these such that this matches, that's these two.
Okay.
So that's a tensor product of the two operators, or an operator product in the physics language.
Mm-hmm.
And then I'm summing over all possible representations that can go in here.
Okay.
That is fixed by the non-zero fusion rules that I have in my
I
ring.
agree. And what is the statement that the B braiding matrix is
Mm-hmm.
a map from this tensor product to the other tensor product? Is that
Yes, yes, yes. It's in fact an isomorphism because it's invertible and so on. But the point is, this B relates this structure to this structure. But now I can take P and Q and then, so these themselves are matrices in alpha 1, alpha 2, beta 1, beta 2, right? But I can put these blocks together so that they shuffle between values of P and Q. That's precisely what this does. And then write this matrix B, which now depends only on the choice of vector spaces here and implicitly the states, the control states.
But what happened to the labels?
These guys?
Yeah.
This is a matrix. So the matrix element of this guy is just B, IJKL, alpha 1, alpha 2, beta 1, beta 2, which takes this basis element here, which is given by alpha 1, alpha 2, and then gives the basis element beta 1, beta 2. This is basically the matrix element of B with these sandwiched. Yeah, I mean, this gives this number.
Okay, I see.
Okay. So now we would like to see one identity that these B's should obey the way they are defined. So I can consider, this is a 4-point conformal block. I would like to consider a 5-point conformal block, where I now have I, J, K. I'm not going to worry about what goes in here. You can just fix them to be vacuum, because B just shuffles these. Let me draw a smaller picture because I need to draw it well. Now I have to get the numbers correct. Okay. So first, I have IJK. I shuffle 2 and 3, which means I take this. So B acts on 4-point functions. So I have to take 4-point function times one more to be my space on which this enlarged B acts, and act as identity on that vector space, but act as B to this usual B in this vector space, which in particular depends on this channel, but I'm going to suppress those because it's all summed over now. So when I do B23, what do I get? I, K, J. And then I do B12. So that's K, I, J. And then again I do B23. So that gives K, J, I. It's completely reversed corresponding to this. This is also the permutation sigma 1, 2, 3. No, not really. Sigma 1, 2, 3 followed by sigma 2, 3. But all right. Now I do another set of moves, which is first to B12. So that's J, I, K. And then I do B23. That is J, K, I. And then I do B12. And I get back this. Well, is it? It's just some properties of braiding, I guess.
That order should be the same as this order.
Yeah, but sure. We cut business.
Yes.
I'm going in the opposite direction.
Opposite direction means what exactly?
I have some.
Let's do it for just two guys.
Okay.
Two guys. So you have chosen some branch cards.
Yeah.
What's your notion of B versus B inverse?
So if I choose this ordering,
yes,
then the only way in which the branch cuts do not meet is this. But if I want to do the inverse,
when you say that, you mean you start with the top operator little below the branch cut?
no, the branch cut goes along with the operator. So the branch cut is a physical thing. The location of the operator is a label. Okay.
I think inverse is just switch on the left hand side and right hand side the directions of the branch cuts.
Okay, but before that, sorry, I'm going to slow it down. When you do your B12,
Right.
okay, I don't know, you might have one consistent convention, but can't I say, when you say the branch cut goes along with the operator, what decides whether you can go one way or not the other? I'm not able to
So
see that.
we have to remain in the same domain of definition
Okay.
and not go onto a different sheet,
Okay.
which means this location of this operator here cannot cross the branch cut of the other operator as it tries to go to its location. So if let's do the perverse thing and try to go this direction. Okay. So at some point there will be a situation where
Okay.
I have,
I'm with you.
yeah.
There will be a situation where their branch
This
cuts
guy
go
will be
together.
this way and this will be that way. So
Okay,
there is
so you can't do that.
the
That's
crossing.
what you mean. Okay,
Precisely.
thank you.
Yeah.
So it has to go this way.
Yeah.
Okay.
And if I want to undo it, I just do it in the opposite direction.
Because now you're below with this guy going that way going.
Precisely.
So you have to do it.
So that is this move here. That's the map.
So the inverse is the opposite move.
Right. Right.
Which is only good if you choose the branch cuts the other way around.
Yes.
Correct.
Yes.
And so the way this diagram is playing out, the
I
initial
choose-
choice of branch cuts is such that the inverse ones
Right.
are aligned with the choice of
The other. Yeah. Yeah.
which will require a little thought from you, but I see.
Or another way of saying this is just cut this here and draw a second thing.
Second. Right.
And this is equal to this.
After wiggling it around. Yeah.
You choose both the same branch cut identities here.
Yeah.
You do two separate moves, not
And
to
then
get
we
back to
finally
identity, but to get back to that thing. That's
Correct.
how you wrote this.
Correct. But somehow here, the fact that these are actual lines,
Actual permutations that
right.
you can move is nice.
right. So I mentioned in the abstract that if time permits, I'm going to make a connection to Chern-Simons theory, and time has indeed permitted me. So I'm just going to make a qualitative.
If we agree to miss lunch.
No,
Oh, is it true?
it's just one statement. One statement, which is that these are not just abstract identities which encode these constraints on the B matrices. The point is, these can be indeed be given a physical interpretation as Wilson lines in 2+1 dimensional theory. And if we cut this at any point, we get we get an insertion of the appropriate vertex operators in this rational conformal field theory. And Moore and Seiberg's claim in classifying this zoo is that instead of studying these constraints, we have a theory which has in one higher dimension, which has much higher symmetry, which is 2+1 dimensional general covariance. And in that case, everything becomes much simpler to understand. And the Chern-Simons rational, and they make this correspondence in which they recover all known examples of rational conformal field theories by starting with Chern-Simons theories in one higher dimension.
Wasn't the Moore and Seiberg paper before Wilson's paper?
That studied these equations.
Yes.
And then they came up with this
Then there was another paper.
called Taming the Conformal Zoo or something.